you are doing something 100 times, but the something you are doing is very different. In the first one, you are flipping coins 100 times, and you're counting the number of heads. We've talked a lot about coin flips in this class. In the second one, you are rolling a 100-sided dice, and you are counting the number of times you got the maximum possible roll. You want to roll a 100. Rolling a 99 does not count. You must roll exactly a 100. So these are two random variables. I call one of them C for coins, D for dice. And we want to compare and contrast these things. In what ways are these things the same? And in what ways are they kind of different? And I have three kind of multiple choice questions here where you choose either C or D or both about which one's a binomial, which one has really small probabilities, and which one can be approximated by the normal, which is what we were talking about last class. Any other questions or comments or anything before I set you loose on this problem? All right, let's give everyone a minute or two to think about these two situations and what we know about them so far. Okay, just a couple seconds left here. I think everybody in the room has answered. Let's see what you said. Which random variable is a binomial distribution? This could have been a question on the midterm. What did people say? Ha! Out of 45 people, 38 people said C, the coins, and only 25 people said D, the dice. And in fact, they both are. So if you said both, you are correct. Only half the people knew that the dice was also the binomial. And that's because we're counting the number of times we rolled a 100. So if you call rolling a 100 a, quote, success, then we're counting the number of successes. This is exactly a binomial. What are the parameters? Well, we're doing something 100 times, so n equals 100. And the chance of the thing we are interested in happening, rolling a 100, that is a 1 over 100 chance. So this is a p equals 1 over 100, and it is an n equals 100. So some people got tricked by that. No, good. We're learning. I think when you put them next to the coins, and I say D the dice, you might think I'm talking about the sum of the dice, which is definitely not binomial, and that's probably why people got tricked by that. But I'm talking about the situation with the dice, but we're still counting the number of things. That's why it's still binomial. Okay, and I have a little picture over here on Desmos, my favorite little graphing app, where I set n equals 100, and then Desmos is animating the value of p. Okay, and I drew it with the bars very nicely. And depending on the value of p, you get sort of these different pictures, right? So on one end, it's the values are over here, and you have this distribution that is spread out in various ways. The dice roll we just said is p equals 1 over 100. 1 over 100, also known as 0.01, looks like that. It's all smooshed onto this side. Whereas the other one, the coin flip, is p equals 0.5. That's the nice, beautiful symmetry in the middle. And they look quite different. So even though they are both binomials, they look a little bit different. And that is the point of this question. That's what we're getting to in the rest of the questions here. Okay, let's go back and see what did people say about these other ones. And let me reveal only the counts. Okay. Which random variable has individual probabilities that are tiny, i.e. the value of the probability mass function, which is the probability you're exactly equal to some value x, which one is tiny. This is exactly related to the very last thing we did on Monday's class. When is it that the probabilities get really tiny? And people said D, the dice. The individual probabilities for D, the dice, are tiny. To answer this question, let's look at the picture. So this is the coins. These are the coins. And again, these are little bars, right? It's like a histogram. The height of the bar tells you the honest to goodness probability. That's the height. So this is the coins when p equals 0.5. And then let's do the dice. That's p equals 0.01. Which one has smaller probabilities? I'll reopen the vote in just 1 minute, now that we have the picture. Last but not least, I want to see this question. Which random variables can be well approximated by a normal distribution, a nice bell curve? Which one looks like a nice bell curve? And people said, hoo-hoo, pretty 50-50. So we're quite a bit split on this one. I'll tell you for sure, in both of these questions, there's only one answer. It's either one or the other, but not both. And we're quite a bit split. Now that you have seen the little adorable animation that I made last night, we can try again. So I'm going to open it up one more time. Now that you see the animation, you know they're both binomials. Maybe now you have a better handle on what's going on, and try to think intuitively of why it makes sense in this situation. Okay, I'm going to reopen it. We're copying the question, and then we will do the answers in just 1 minute. Okay, duplicate, and I'm going to the duplicate. Okay, it is open again. So I'll give you another minute and a half to try again. Now that you've seen the picture, maybe I'll leave the picture on the board while we're going. This will inspire you to see what's going on. Okay. Okay, just a few seconds left. I think there's like 2 people who haven't answered yet, but we'll see if they get in on time. Okay, there we go. Okay, so this time, was everybody awake when I said the answer is both? 10 people were still asleep. Okay, so but this one is both. Both were binomial. Now, which one has the tiny probabilities? This one you can very clearly see the answer on here, right? So the coin flip is somewhere in the middle here with this very, very low coin flip. We saw that last time. As you do more and more things, it gets more and more spread out, and then the height has to go down to 0. That's why the continuity correction is not super useful for big things. But let's see if you guys figured that out. All right, so 31 out of 46 people said it was the coins, and the coins is correct. In this problem, the dice do not have probabilities that are very small. Actually, the dice have some big probabilities. If you look at the situation 0.01, 0.01, that's the dice roll, all of the probabilities are basically happening here. Like the chance of you rolling more than 10 100s is so extraordinarily small. All of the probability is being taken up in that first little interval. So sort of 0, 1, 2, 3, 4, and 5, that accounts for like 99% of the probability. The most likely thing is that you're going to roll 1, but also rolling 0 is quite likely as well. So when you do something that is sort of rare, even if you do it 100 times so that on average you get like 1, most of the probability is living here on the small numbers. And the individual probabilities are not getting small. They're not small numbers like they were in the other situation. So this is another way in which the coin flips are different than the dice rolls. Let me write some of this down so that we record some of these ideas. So we're comparing the number of roll 100s in 100 trials. This is the dice situation versus the coins situation, the number of heads in 100 trials. And both of them are binomial. This one is binomial with n equals 100 and p equals 0.01. And this one is binomial with n equals 100 and p equals 0.5. So what we're really doing is we're comparing and contrasting what happens if the p-value is really, really small versus if the p-value is large, where p here is the probability of success. P equals the probability of success in a binomial success. Okay, and so the picture is like this. This one is centered around 50, but is spread out. The spread is very large, so it kind of looks like this. It's very, very short, not very tall at all. And we saw that. In fact, you could calculate the standard deviation here. I believe will work out to be 5. The standard deviation, so the variance, is n times p times 1 minus p. Like we talked about last class, 100 times a half is 25. And if the variance is 25, then the standard deviation is 5. So sort of most, one standard deviation is to 55 and to 45. So that's the kind of thing we were doing last class, is these kinds of approximations. Maybe there's a question that says, please find the probability that you rolled between 45 and 55 heads. You flipped between 45 and 55 coins. And you would turn that into sort of this kind of, that's minus one standard deviation to plus 1 standard deviation. So that would be approximately, so the probability, the number of heads, what I call that, C, is between 55 and 45. That would be approximately the probability that your Z random variable, the standard Gaussian, is between -1 and 1, which is some famous number. Is this one 68%? I never. 68.26. See, the real ones have it memorized. 68.26. Yes, you see, I covered my butt by doing little squigglies. And the squigglies mean this is only approximately this. So this is not exactly this. It's approximately this. But this one really is 68.26%. That's one of those famous numbers on your thing. Okay, that's the coins. Actually, you know what? I think I've sort of spoiled the answer to the last mathematize, so we might as well go back and do this one as well. Which one is approximately a normal distribution? And this one, look, 85% of people knew it was the coins and not the dice, which is fantastic, because you probably noticed on the picture that this does not look like a normal distribution. So this is the point over here, that this one does look normal. So yes, normal. I'll say normal-ish. But the dice, it's a very different situation. So the dice kind of looks like this. All the mass is kind of bunched up around here at 0. So I draw it kind of like this. So and the percentages are not getting really small. So over here, all the percentages individually, they were quite small. I think they were all like 5% or less. So as it's spreading out, the total height has to go down. But over here, it's all bunched up near 0. And so the height is not going to 0. In fact, I believe, if I recall correctly, the first column, the probability of a 0, is 37%. 37%. Let's see if I remember that one right. That's the one I remember. Okay, well, look at that. It's between 30 and 40. It's a little higher than 35. It's a little less than 37%. There's a magical number that this is close to that I will put in now, and it's the number 1 over E. Y equals 1 over E, 36.7%, and it should be extremely close to this. So this is 36%, this is 37%. We're at 36.7%, and the real answer, the 1 over E is 36.78, just a little bit higher. We'll see why this is later on, but this is a typical kind of thing where the percentages don't go down to 0, the percentages stay large. Okay, well, let's get rid of 1 over E for people who are scared of the E. Now that's kind of a bonus. So they are not getting small, not getting small. The individual probabilities stick around. Okay, and this one, it is yes, getting small. Okay, and because could calculate all sorts of things. You could calculate the standard deviation and so on. But the real thing to notice is the picture is totally different. So the real conclusion is no, this is not normal-ish. And in fact, we could put on our normal approximation. So I put this on, I called it G for Gaussian. And there's the nice bell curve that I drew in green. And for large values of p, it works very nicely. So this is what we were doing last class. We were saying, hey, look at how beautiful this thing is, right? The green bell curve goes right through those probabilities. And if you want to calculate the probabilities, the area under the green bell curve is a very, very good approximation for summing up the areas of these bars. And that works really nicely for the big numbers. But then if p is too small, p is really, really tiny. Oh boy, oh boy, oh boy, oh boy. Wow, let's look at it now. Is this a good approximation? Let's go back down to 0.01. And let's try to zoom in on the axis a bit here. Look at this. Let's try to fit the whole thing in. Is that green curve a nice approximation for these blue bars? Well, not really. Not really. First of all, it's very asymmetrical. So the green curve is perfectly symmetric, and the blue bars, the actual thing we care about, is not symmetric. So this is a thing to write down. Not symmetric. Not symmetric. And the other thing that the normal gets quite wrong is the normal distribution is estimating that we can get a negative number here. So saying like you have a pretty good chance of getting -1 rolls of 100, which we know is impossible. So the normal distribution is not a good approximation here. So last class we told you, yes, the normal distribution is a great approximation sometimes, but this is not normalish in this situation. You might?
Professor Nika.
Oh, no, yes.
I got a question.
Yes, please.
What if you cranked up your n big?
Ooh. Oh, that's a good idea. So here's a good question. So this is, which situation will happen? Will we be in this situation or this situation when we do what is suggested? This is like, what happens if we crank up n big, okay? And now the answer is going to be, as always, with everything in life, is it depends. It depends. And it depends on what you do. So in my original question, I said, you roll a 100-sided dice 100 times. We're counting the number of times you got the maximum value, all right? If we are cranking up n big, do I crank up the number of times I rolled it? Or do I crank up the number of sides of the dice? Or do I crank up both? And this is a very reasonable thing to do. So let's do two situations. Let's do n big. So we're going to do n big, where n is the number of times we roll it. Number of times we roll it. But we can either fix p. We can say p equals 1 over 100 is fixed. So always roll a 100-sided dice. Just roll it more and more times. Or maybe the fair thing to do, if I saw this question and someone said, please generalize this question to a 1,000-sided dice, I don't think it's fair to roll a 1,000-sided dice 100 times. I think you should roll the 1,000-sided dice 1,000 times. So the whatever sides of the dice, you should roll it that many times. That's the exciting thing. So that's the other possible situation. So you could say p always is 1 over n always. Those are the two ways I think you could generalize this. And let's see what happens in these two situations. So what if p equals 1 over 100 and n is fixed? That's easy to answer because I could just make the slider go all the way up to 1,000 here or 10,000 and make it really, really big. And we can see what happens. Let's turn off this. I guess we leave the Gaussian. So here we are. This is the 100-sided dice rolled 100 times. But what happens if we roll the 100-sided dice? So we're going to leave p equals 1%, but crank it up all the way up to 10,000. We're going to roll this dice more and more and more. Let's see what happens. Okay. Look at that. It immediately spread out. Oh, no. Did my computer crash? No, it did not. Okay, we're coming back. Okay, I think maybe 10,000 was too ambitious. Let's try 1,000. So there you go. If you roll enough times, it starts to look like the coin flip situation. So if you roll it enough times, even with p equals 1 over 100, it really is the average of the coins, or the dice rolls in this case. That is n times p. And if n is getting bigger and bigger, and p is a fixed number, then this will eventually get really big. This will go to infinity as n goes to infinity. And that will eventually look like this situation. So if you have a really big n value, even if the p is really tiny, as long as n times p is big enough, it will start to look like this situation in green over there. On the other hand, what happens in this situation when p equals 1 over n? You see, I can rig this one up in Desmos too. Instead of putting in p equals 1 over 100, I can just put in the formula p equals 1 over n. Okay, let me move this thing back down to 100, and then let me put in p equals 1 over n. And there's my blue. This is what we had before. And now I can make n bigger and bigger. We can do more and more sides on our dice. We can do a 1,000-sided dice, but rolled 1,000 times, and we can see what's happening there. Let's hit play. 3, 2, 1. Is it not working? What's going on? Wait. Something happens right at the end. So look, when n equals 1, that's a one-sided dice. Hey, if you roll a one-sided dice, you're going to get the top value one time. What about a two-sided dice? Can I figure out how a mouse works? A two-sided dice looks like that. Okay, two-sided dice. That's a coin. Hey, that's flipping a coin twice. What about a three-sided dice, and a four-sided dice, and a five-sided dice, and a six-sided dice, a seven-sided dice, eight-sided dice? Hey, this is not looking very different. Once you get to about 11 or 12 sides on your dice, it might as well be 1,000 sides on your dice, or 100 sides. It really does not change very much. What this is saying is it's getting closer and closer to something. As the number of sides gets bigger and bigger, it's getting closer and closer to something. It's just that the something is not the green Gaussian distribution. It's something else. Oh my goodness gracious. What is going on here? So when n is big and p is 1 over n, one hint that something is settling down. If you look at the average, that is p times n, that is always 1. So in one situation, it's going off to infinity. It's getting all spread out. In the other situation, it's settling down. So actually, it converges to something not Gaussian. And this is the same kind of convergence idea we saw with the dice rolls many classes ago, but something non-normal. An abnormal distribution, perhaps? No, this is why the normal is a very dumb name, because I just mean it's not the normal distribution. There's nothing wrong with this distribution. It's a perfectly good one. And that's the topic of today's lecture, is we're going to study this distribution in a little bit more detail. This distribution has a special name, and it comes up in these situations where you have a lot of trials, and the probability of any individual trial is super duper tiny. But they're balanced so that you get something cool coming out in the limit. And so the normal distribution doesn't work very well, but I have colored in the approximation, which is this formula, and I've colored it in purple. And there you go. It's that purple distribution is a much better approximation than the green, and you can see it works quite well. I think if we can go just all the way up to n to 1 to 20, you'll see that even by the time we get to 20, it's converging, getting really close to that purple distribution. So the blue is the actual binomial. Blue for binomial. Green was for Gaussian. Purple is for something that starts with a p. Somebody typed it in mathematized last time. The purple distribution is called the Poisson distribution. Poisson distribution. And that's because it was first discovered with fish. The purple distribution is called the Poisson distribution. Okay.
Now, Professor Nika, you know you told a white lie there.
Oh, no, yes, okay. Well, it's sort of named after fish indirectly. So there's this guy. Let's look up this guy. If you search for Poisson, okay. I guess my Google might be different than your Google. What happens when you search for Poisson? So first of all, it translates it to you. It does mean fish. Why can I not zoom out? Okay, Google won't. Google has crashed. Well, this is the guy. This Simon Poisson was a French mathematician and physicist. It's named after this guy. This guy discovered it. I think this guy was named after a fish. So indirectly, this thing is named after a fish. Maybe his grandparents were fishermen or something. Now, can I zoom out? But there you go. So Poisson means fish. And we're talking about the Poisson distribution, which is named after this French guy. Yes. Okay. What to say about the Poisson distribution? Well, you know the basics now, which are, let's see if we can find it. Mathematize. Okay. Well, okay. you know the basics. It's a distribution that the binomial gets closer to. I'll have some nice things on R that Professor Humphrey will show you in a second. But I think the thing I wanted to show you was that don't get mixed up between the Poisson and the normal. They are two different limits of the binomial. There's this limit where the n and the p are in such a way that it's all spread out. So the n times p is extremely large, and it's all spread out, and it's Gaussian. And then there's this other one where the n times p is a small number and is not growing, and that's the Poisson. And there are two different possible things you can get depending on the situation, and you have to know when to use it. So no, not normal-ish, but yes, Poisson-ish. Poisson-ish. Okay. Maybe we'll, this is it for my theoretical thing. We're going to get some more nuts and bolts in a second. Are there any questions or comments at this point about the new thing we're learning? Okay, let's see some R things or some applied things about the Poisson distribution now.
I'm connected. What do I need?
Oh, we need to press the HDMI button?
HDMI button.
Okay, there you are.
Okay, so before we give you the Poisson distribution formally, I will tell you that it is a model for rare and random events. And what is the concept of a rare and random event? Well, there's a couple things I think are interesting to think about. One of the things, of course, as living organisms, what we like to do, we don't get to do it forever, but we like to avoid getting killed. Okay, would we agree that that is something that is always in our best interest, right? We like to not get killed. We don't like to get killed. We also don't like to get injured. And yet, as we know from watching the news, terrible things happen to people all the time. So, you know, life has risk to it. And, you know, it has risk to it. We have to balance our risks in the sense that, you know, if we don't take any kind of chances, we don't get anything done. If we don't drive anywhere, we don't get anywhere, right? But when we drive somewhere, you know, there is a risk of an accident along the way. If we want to take a vacation and, you know, you know, let's suppose we decide we were going to go to, I don't know, say Brazil. It's a long way to walk. Also a very long way to swim if you don't want to take it via the thing, and even a boat would take a long time. So you'll probably fly. And, you know, there is a risk that planes will crash. Planes have been known to crash. The relative risk is an interesting question. And of course, plane crashes for the number of flights are extremely low. It's considered the safest way to travel, at least for long distances. Of course, we have a psychological aspect of risk on that one because once we're in the plane, we really have no control over what happens in the plane. We often feel that we have more control when we're driving, and part of that is true and part of it is maybe not so true. Anyhow, this particular website, I just grabbed this one as kind of an interesting thing to talk about how we think about risk statistics. And it's from the United States, NSC, injury facts, your odds of dying from an accidental opioid overdose continue to be greater than dying in a motor vehicle crash. Okay, well, let's just think a little bit about that statement about the odds being dying from an accidental opioid overdose than in a motor vehicle crash. Is that really true? Could somebody tell me why they would have a problem with that statement? What do you think? Yeah, so if you don't use opioids at all, do you think you're going to die from them? Right? So that's kind of an important idea. Similarly, of course, you're not going to die in a motor vehicle crash if you never go in a motor vehicle. But most of us end up going in motor vehicles, but probably a relatively small proportion of us are into opioids, but I won't speculate what percentage that could be. Okay, so in the US, they got various odds of dying. Let's just look at a couple of them and ask appropriate questions or ask some questions about there. Your odds of dying from a preventable injury, unintentional, is 1 in 19 versus dying from being assaulted with a gun.
Wait, hold on. What is this? This is one of the things that drives me crazy. What do they mean by 1 in 19? The
That's what
probability
we will
of
come
something is 1 in 19. What is the something?
What is that something? Okay.
Okay,
so,
good. I'm glad. I thought
so
it
we
sounds
look
like,
at the
oh my God.
statistics. Okay. And let's go to the opioid overdose there. 1 in 57 versus dying from electrocution is a little over 1 in 14,000. Or about 1 in 14,000. Okay, and you got some other statistics here. Let's just go through a little bit more of these. Motor vehicle crash, 1 in 95, it's approximately about 1 in 100. Dying in a plane crash is, they say, too small to calculate. I don't believe that it's too small to calculate.
Depends how good at math you are.
It depends how many decimals you're willing to go, right? Like what's this about too much?
It's like if someone could write that on their whole exam.
Yeah, yeah.
All these numbers are too small to calculate.
Yeah, exactly. Walking down or crossing the street, 1 in 471 versus being stung by a bee, hornet, or wasp, about 1 in 41,000. I've actually known a person who died from being stung by, well, they said it was bees, but I'm almost positive it was yellow jacket wasps. So there's a bunch of them. Bicycle crash, then by fireworks. Drowning in a bathtub, that's about 1 in 6,000 versus about 100,000, about 1 in 100,000 for being in a flood. Okay, so Professor Nika raised the question, what do these numbers mean? How do they come up with those numbers? And it's kind of good. They actually explain how they got their data or how they came up with those numbers. And let's just kind of take a look what they did here. So the first thing we need to see is that these are lifetime odds, okay? It wasn't a per year rate or anything like that. It was a lifetime odds. So basically what they did was they took the 2023 U.S. population of about 335 million, and then they did, they got the they worked with the life expectancy of a person, 78.4 years, and then they took the single year odds and based on tables of death. And so these were lifetime odds that they were giving you. And of course, we can ask whether some of those, is that going to be kind of constant over a 78-year period? Well, the odds of dying from an accidental opioid drug overdose in 2023 were 1 in 4,436. So they took the number of people who died of opioid overdoses in 2023 and divided that by the population size. And then they would have taken that and multiplied by, the 78 years lifetime expectancy. Although we have to think that a lot of young children aren't on opioids. Anyhow, it's kind of rough where they kind of got some of these numbers, but nonetheless, they are things to think about. So one of the other things to think about in probability, and we're kind of discussing this, is that the fact that on the lifetime risk of a randomly selected person from the United States dying from opioid poisoning was 1 in 57. That risk varies tremendously. For a huge chunk of the population, it is in fact 0 if they never used opioids. Okay, so we operate in that in our everyday lives as we seek to minimize risk and we trade off risk and expected gain. That's really kind of the two Two key things, not the only things that we really worry about, is probability and expected return, expected benefits, costs and benefits. And so, Christmas time is going to come up, and who knows what the weather's going to be doing, and there's probabilistic aspects of that, and then we'll decide is it safe to drive, and the weather could be a little bit crappy, so your risk goes up a bit, and you kind of weigh that versus the fact that you want to get to see family, that kind of thing. So we're constantly making trade-offs on probability and making this kind of cost-benefit analysis and looking at how we improve our odds for good outcomes. Some things we can do readily. Certain things, the things that eventually cause our demise, things like cancer, heart attacks, that kind of thing. Some of that we can do things about. Some of the things are like our genetics, we have much less control over. But we have much more control over the odds of many things than we, we recognize we have control over a lot of things, and then it's a case of whether we're going to exert that control. So next thing I want to do is go to give me a freeze on that for a moment. Just give me a freeze. Just got to see if that. Oh yeah. Yeah.
Well, we're looking at this next thing. I'll show you. There's a Wikipedia page I really like for this kind of thing. It's the Wikipedia page on micromorts, and a micromort is a unit of measure. If you know Latin, you might know micro means 1 in a million, and mort means death. A micromort is a 1 in a million chance of death, and you can quantify all these risks as micromorts. So in Canada, you have 20 micromorts per day of risk. So you're just walking around, you get 20 micromorts per day of that includes all the deaths in Canada. You have a 20 in a million chance of dying per day. If you do various activities, you can rack up some more micromorts. So for example, if you go scuba diving, you get 5 micromorts for a scuba dive, which doesn't sound too bad. If you're some kind of elite scuba diver, that's also, you get 160 per year. But the one I was impressed by, this one always blows my mind. Skydiving is 8 micromorts per skydive. But skiing is 0.7 skiing. If you go skiing for 1 day, that's 0.7 micromorts per day. So if you go skiing for 10 days, you're about as likely to die as if you'd gone skydiving once, which I think is very interesting. Okay, and you have all sorts of things. These are useful for, here's another one I really like for travel. If you go by motorcycle, you can go 6 miles and before you get 1 micromort. But if you go by airplane, you can go 1,000 miles before you pick up 1 micromort. So again, we're talking about these really tiny risks, rare events, and that's why we have to use the math not of the normal distribution, but of this Poisson distribution. That is like, if you have a really small chance of dying on any individual day, but you're around for hundreds and hundreds of days, how many bad accidents will you have? So that's this distribution that does rare events. Okay, yeah, let's go back to the slide here, and you can see the proper name. And here is the formula for that purple curve. Here, actually, maybe we should leave the purple curve on the board while you tell us the formula.
Curve on, it is. So we'll start off by just laying out the probability distribution for you. And we'll express it this way. It's the probability mass function. This is a probability mass function because the random variable x, which we'll define in a moment, takes on values of 0, 1, 2, and so on up to, it takes on countably infinite number of values. And the probability, depending on how you wish to express it, some will use a mu in there, but probably the most common expression is to use a lambda. We'll explain lambda in a moment. E to the negative lambda to the x over x factorial. It's kind of a funky equation. And we could have added a 0 otherwise because these are the only values of x that we can get a
Here,
non-zero
let's,
probability with.
Let's show the students what this lambda does. So here, I called it L in Desmos, and if you make the p-value, instead of being 1 over n like I did before, if you make it L over n, then this purple thing is the lambda. The blue, remember, is a binomial that is really close to this thing, but the nice thing is I can slide this L value up a bit now. So these are the Poisson distribution with different values of lambda. When lambda equals 1, you get this classic curve with the 37%, the 1 over e. If you take the formula on the board over there and you put lambda equals 1, you see there's an e to the minus 1. But for bigger values of lambda, it'll start to look like this, and it approximates the binomial in all these situations where the p-value is really, really small, but the p-value is lambda over n.
And
okay.
it's worth pointing out that the lambda can, in fact, be less than 1.
Oh yeah, it can be any. That's a good point. It can be any number. Let's make it.
Well, not any number.
Any positive number?
Any positive
Okay,
number.
thank you, yes. So there you go. There's a lambda of 0.011. You're almost, you're very likely to have 0, but you could have 1. Okay, very good.
Okay, ever onwards. So what is this random variable? It is often described as the number of occurrences of a rare and random event, often in time or space, okay? And so we'll give you a couple examples in a moment. So think of this idea of rare and random events. And that lambda is the only parameter in the Poisson distribution. It is the mean of the distribution. So what we were looking at is, the number of occurrences in some unit of time, some unit of space, or some combination of time and space. We call them often spatiotemporal sampling units. And so there's an example, some examples of Poisson events, at least approximately, okay? Number of parachute accidents per week or per n jumps. We could do it per n jumps. We like to think that when people jump out of a parachute, they have a very high probability of surviving. Has anybody jumped out of a parachute? Yeah? And did you survive it? Yeah, okay, that was good. Had anybody else not jumped out of a parachute and want to jump out of a parachute? Yeah, okay. Okay, you see that is something you have control over. So if you don't jump out of a parachute, you will definitely not die from parachute
Has
jumping.
anybody gone skiing for more than 10 days?
So parachute jump accidents are actually something I find kind of fascinating because every now and then I see one of them happen. Okay, so let's just think about this number of parachute accidents per week. Are those rare and random events? Well, they're certainly pretty rare events given the number of parachute jumps that actually occur. And we'd have to think they're pretty rare because otherwise people wouldn't be jumping out of parachutes. At least we think that would be the case. Are they random? Well, maybe not totally true in the sense that every individual fatal accident, are they always independent of one another? Well, can you give me a reason why you think they might not be independent? What do you think? Skydive in pairs and they get their parachutes tangled and they both go plummeting to Earth. Yes, that's definitely a case of non-independence, right? And it happens. Okay, so there was that. And so something like, industrial processes, they're manufacturing cloth and maybe they're counting the number of flaws per square meter of cloth. And you wouldn't expect very many flaws in a square meter of cloth because otherwise they got serious problems in their manufacturing. But, every so often there maybe a flaw shows up. Typographical errors per page in a book, something like this. Again, they don't make very many typographical errors, but they could be counting how many per page. Again, quality control is seeking to reduce that. And very classic one, if you're involved with physics at all, is number of radioactive particles that decay in a particular time period. So those are just some of 3 examples, and there's so many examples of the Poisson distribution being at least a very good model for the phenomena under study. So just got a couple extra little points in here. Another interesting thing about the Poisson, we will just state without proof, is that lambda is also the variance of a Poisson distribution. So that's really quite funky. Its mean is also its variance. And as Professor Nika has already been working on, and if you kind of noticed his equation for the Poisson, where I have lambda, he had NP in there. And what he has used is a Poisson distribution can be used to approximate a binomial distribution with large N and small p. And the way we do that is we set lambda equal to the mean, which for a binomial distribution is N times P. And a general rule of thumb is that your NP is going to be less than or equal to 5. Okay? It's, again, a rule of thumb. You're typically going to have a pretty large N and a pretty small P. You're not going to do it with N equals 10 and P equals 0.4, for example.
Well, and like we said last class, if N times P is very large, then you use the normal distribution. So you're kind of covered.
And then there's situations where N is small, and it doesn't really matter what P is. It's just go calculate the binomial.
Then you do it by hand, yeah.
Just do out the binomial, yeah. So you can use computer software such as R, an online calculator, to obtain individual and cumulative probabilities for the Poisson. Maybe we'll do a few of those next day. Yeah, but we won't do those today because we have limited time. But we can work through a pretty quick example here is how many have been whale watching? Did you see whales? Has anybody ever gone whale watching and missed seeing your whales? Okay, so whale watching tours, I mean, they're very good that they make sure they go to spots where you really are seeing whales, but we can imagine that there's some ocean bay where whales get seen relatively infrequently. Well, not all that infrequently, but let's suppose they occur with a mean occurrence of 1.2 sightings per day. And if we could assume that this meets the condition for a Poisson, in other words, rare and random events, we can work out the probability of no whales, exactly 1 whale, at least 2 whales. So let's just do one of these anyhow. Maybe we'll get to 2. On a randomly selected day, what's the probability of selecting? Okay, so we're going to go to, leave that question. I need my dock camera. Okay. Oh, absolutely excellent. What excellent timing. Okay. So, whale example. So I'm going to put it this way. X equals the number of whales sighted on a given day. And what we're saying is X is, we're going to treat it as Poisson with lambda equal to 1.2. And our very first question, probability of no whales, the probability X equals 0, which is P of 0, is going to be e to the negative lambda to the x over x factorial, which when x equals 0 simply comes down to e to the negative lambda, which is 1 over e to the lambda. And so that is going to be e to the negative 1.2. And I'm just going to note that lambda to the x over x factorial equals 1 when x equals 0. Okay? So you can work out that number. We have hit ourselves at 20 after right now, so I don't want to go on any further. On your own, try to do the next two. I think we'll use one of those to start our mathematize. Maybe we'll use both to start our mathematize on Friday.